When I think about exponents and polynomials, and in my experience being involved with a course like Math 95 for many years, I think the biggest thing that takes some wrapping your head around is to answer the question, when do exponents change when you're simplifying an expression, and when do they not change? So one way to think about when exponents don't change is they don't change if we're just evaluating if we're just using them to evaluate an expression. So here, 7 to the power 2, what is 7 to the power 2? 49. Yeah. And so there, it's not as though an exponent has changed, it's just that I've used that exponent to make my numerical expression simpler. Then I would carry out the rest of the arithmetic that's here. What would be the next step if I have 1 minus 3 times 49? Multiplication, exactly. By the way, the common error for somebody looking at this is they read it from left to right and see 1 minus 3. Ooh, I better do 1 minus 3 right now. Order of operations tells us that subtraction doesn't happen until after multiplication. So the first thing we ought to do here is 3 times 49, which is 147. And then I'll do 1 minus 147. I'll spare you the arithmetic on that to give me negative 146. So there, our exponent didn't change, it just became a part of the expression that we were evaluating. But I want to take it a step further than that. So that was an example that didn't have any variables in it. I want us to get into the examples where we do have a variable expression with variables and exponents in it that we're interested in simplifying. So maybe let's try this. We're going to see examples of a couple different kinds today. And I just want to kind of contrast them for just a moment. So let's suppose that I have something like 2x to the power 3 and, I don't know, 5x to the power 2. And let's suppose that I take these two expressions, each of which, by the way, is called a monomial. By the way, what does the prefix mono mean in this context? Whenever you see the word mono, what does it mean? Yeah, Steve's got it. It means one. So monomial means that there is one term in each of these. The term here being 2x to the third. The term over here being 5x squared. So I have this pair of monomials. Each one of them has the same variable in it, x, but the variables have different exponents attached to them. Maybe I'll actually... Let me revise this. Let me give them the same exponent, because I want to try to do some contrasting here. So I have two monomials. Both of them have the same exponent, the same variable. They have different numbers out in the front of the variables. Remember, we call those coefficients. So the coefficients are 2 and 5. Okay, so the distinction that I'm trying to surface here, I'm going to also write the same monomials again over here on this side. What I want to get us thinking about is the arithmetic that might appear in between these pairs of monomials. For example, on the one hand, we might think about multiplying them together. On the other hand, we might think about adding these monomials together. And so now my question is, in which of these two situations, so the situation on the left where we're multiplying these polynomials and the situation on the right where we're adding them together, under which of those circumstances will the exponents not change? What do you think? I think when we first start talking about these, some bells are starting to ring for people, right? That when we multiply together two monomials that have the same base, we're talking about that variable x here that's the same in both of those monomials. When I multiply those monomials together, what happens to their exponents? Spencer? They add, so they probably change in that case, right? My monomials that began as having an exponent of 3, if I were to multiply them together, multiply these two monomials together, the exponents 3 and 3 are going to add together. So when two monomials with the same base are multiplied by one another, their exponents add. And so that's going to be the first place where I'm going to write exponents change when monomials multiply. And the caveat there being that the base, the variable, has to be the same. And so the example we have down here, 2x to the third times 5x to the third. What am I going to get when I multiply those two monomials together? First of all, how many x's am I going to get in my product? 6. 3 plus 3. Right. So that's where the exponents add together. And that gives me my new exponent. So my exponent has changed. What's my coefficient? How many x to the 6 am I going to have in my product? 10. Where'd the 10 come from? 2 times 5. Right. So another thing to remember here is that we end up doing different type of arithmetic with the exponents than we do with the coefficients. The exponents up here, up in exponent land, right, they added together where the coefficients multiplied. Okay. So the coefficients are on the level in a way, right? The coefficients are doing the same thing that the two monomials are doing. I'm multiplying the monomials, and so I'm multiplying the coefficients. The reason for that is that multiplication is both commutative and associative, and all of that means is that I can rearrange the order in which I carry out these multiplications so as to get that 2 and that 5 together, and so as to get the 2x to the thirds together as well. So I'm just going to rearrange it and take away the parentheses. We can do that because multiplication has those nice properties. And when I do that, I can see that, oh, I'm really just asking what is 2 times 5. That's where my 10 comes from. But then on the other hand, where the real action is here. Whoops, wrong color. The real action is right here, where we multiply the 2x to the thirds together and add the exponents to get x to the 3 plus 3. So the first answer is exponents change when monomials are multiplied. Expand on that just a little bit. So why do these two exponents add together? If you're in doubt, and this is something that I've helped a couple of you to do in some of these problems early in the semester already, if in doubt, remind yourself, what does x to the third actually mean? What does it mean to raise a quantity to the third power? Yeah, we're going to multiply it by itself a total of 3 times. And then likewise for this other x to the power 3 is also x multiplied by itself a total of 3 times. And so if I multiply x to the third multiplied by x to the third, all I'm really doing is I'm counting how many total factors of x I have in that product. And if I count up the total number of factors that I have, I'm going to find that I have 1, 2, 3, 4, 5, 6 factors of x. Right? So that's the explanation for why the exponent rule works. This exponent rule works the way that it does. At least that works the way that it does when the exponents are positive whole numbers, right? It would be a little scary if we had x to the negative 6 or x to the positive 2.5 or some weird thing like that, right? Because then we wouldn't be able to just sort of write it out the way we do here. The good news is the addition rule still works even when the exponents are negative or when the exponents are fractions or when the exponents are anything nasty. We're going to do a little bit with exponents that are fractions later on in our run through the beginner level of course. We'll do a little bit more with negative exponents probably in the second run through the course. You'll see some today, but we won't actually do any manipulation with them today. So if in that example the exponents changed, let's talk about when the exponents wouldn't change. When do exponents not change? We decided they changed in this example right here. What about the example on the right? Right. So in the example over here, 2x to the third plus 5x to the third, how do I understand what that is? So when I add these two together, so exponents never change when monomials are added. Instead, what happens? Spencer just said it. In 2x to the third plus 5x to the third, what do I end up with? Well, if the exponents aren't changing, then how many powers of x do I end up with in my sum? Yeah, so there my exponent stays the same. But what changes are the coefficients. So what I'm really saying here is I have 2 copies of x to the third on the left, and I have 5 copies of x to the third on the right. If we want to understand this in the same kind of expanded notation that we did the other example a moment ago, we could do that as well. Because what is it to multiply something by 2 other than to add that thing to itself, right? We're just doubling x cubed. So 2x to the third we can think of as x to the third plus x to the third. Likewise, 5x to the third is the same thing as adding x to the third to itself 5 times. X to the third plus 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 x to the third. Obviously, you're not going to write all this out every time, but if it helps you to remember what to do in the general case, by all means, This is a concrete example of what it looks like. So that if I take 2 copies of x to the third, 2 multiples of x to the third, and I add them to 5 multiples of x to the third, all I really need to do now is to count how many multiples of x to the third I just wrote. How many did I write? 7. So since I have 7 copies of x to the third, 7 multiples of x to the third, what is my sum going to be? 7x to the third. Yeah, right. What name does this process go by? What's the buzzword that you think of when we do the process like we just did up here? What do we call that? What do we call the things that we just combined? Like terms, exactly. There's the buzzword, the vocab that goes along with this, right? So monomials that are added together preserve the exponent, in this case x to the power 3, because those two were like terms. So let's just remind ourselves what it means for 2 monomials to be like terms. So how would we have known from the outset that 2x to the third and 5x to the third were in fact like terms? What is it about them that makes them like terms? They have the same variable on the one hand, and?
They have the same exponent.
Yes, right. So both of those have to be true. They have the same variable, in this case x, and that variable has the same exponent in both cases. Right? So in fact, the only thing that's different about these two terms is what? The number, the coefficient that's out on the front. Spencer. One of the keys in sorting out this process is that we can take a product, we can multiply 2 monomials that have the same the same variable but different exponents. We could make that product simpler. So for example, let me just tweak the one we did a moment ago. Let's say I had 4y to the second power multiplied by 9y to the fifth power or something. We can actually make that simpler. First of all, how many powers of y would we get? There we would add the exponents because we're multiplying 2 monomials, so y to the 7th, and the coefficient would be 4 times 9, 36. So in that case, we had different exponents and we can actually make them simpler. Although the variable was still the same, right? The variable was y in both cases. So different exponents can simplify when multiplied. There's a little x there for multiplied. But on the other hand, if I were trying to add those two together instead of multiply, 4y squared plus 9y to the 5th, then what would I do? I would do the best thing ever.
Leave it.
Nothing. Right. Leave it. There's no possible way for us to simplify this expression any further than it already is. Because 4y to the squared and 9y to the 5th are not like terms. And so it's like playing with 2 different sets of Monopoly money. On the one hand, I've got $100 bills. I've got 4 of them. On the other hand, I have some $1,000 bills, $10,000 bills. I've got 9 of them. And if I stack them all into one stack, then I have 13 bills, but they're not 13 of the same bill. So I can't combine them together and say I have 13 $10,000 bills, or that I have 13 $100 bills, or that I have 13 $1 million bills. None of that makes sense. They're 2 bills of 2 different types, even if they're in one stack. So if they're like terms, we can combine them by adding their coefficients. But if they're not, then we have to leave them just the way we find them. There's nothing we can do to add or subtract terms that are not like terms and make them any simpler. Big distinction is that like terms are necessary over here when adding or subtracting in order to make things any simpler. Like terms are not necessary over on this side, because in those cases, we can actually change the exponents to fix the fact that we don't have like terms, when we don't have like terms. Okay, so now we have that first set of examples down, and we see that the most important thing that differentiates the left side of the screen here from the right is the type of the arithmetic that's happening to the monomials. On the left side, we have multiplication happening. On the right side, we just have addition. So on the right side, we have arithmetic that's simpler. On the left side, multiplication is a more complex operation. But here's the good news. If exponents change when monomials are multiplied, what's the other circumstance where we know for sure that exponents are probably going to change? If multiplication changes them, what else does? Division. So let's get that down. I promised that this one would be quicker. So exponents are probably going to change when monomials are divided. So then the question is how? So let's come up with an example again. Let's do 16a to the power 8, and then I'm going to divide by, I don't know, 2a to the power 5. So how are the exponents going to change when I carry out this division? What do you think? Subtract. Right. Why does that make sense, by the way? When we multiplied monomials, what happened to the exponents? We added them, right? I should write that down up here because this board is sort of incomplete without it. Add exponents when we multiply monomials with the same base. And so why does it make sense then that in the case of division we would subtract? How would you explain that to a 5-year-old?
They're opposites.
Yeah, exactly. Because division is the opposite of multiplication. What happens to the exponents under division is the opposite of what happens to them under multiplication. Right? So if we add exponents when we multiply, we're going to subtract exponents when we divide. That's all there is to that. It's not having to remember two different things, but two related things. So we'll take 8 and 5, and as we said, subtract the 1 on the bottom from the 1 on the top. 8 minus 5 is going to give me 3. Now, how about the coefficient? 16 on top, 2 on bottom. What's going to happen with that? All right, we're just going to treat that like it's an ordinary division problem. 16 divided by 2 is going to leave me with 8. So exponents do change when we divide monomials with the same base. When we divide monomials, the exponents subtract. Playing the opposite game one more time. If exponents don't change when monomials are added, then when else do they not change? Right, when monomials are subtracted. Now, this also applies, and here's where I want to just add one last layer to this conversation, is that I'd like to also get us past just working with monomials. I'd like to also get us working with what are called polynomials. So if a monomial was something with one term, a polynomial is something with multiple, possibly 2, possibly 3, possibly 10, right? Right, so a polynomial is just a monomial with several terms. And if it has several terms, that means that there are probably several unlike terms, right? Because if they were like terms, we could just combine them together and call it a monomial again. So let's do an example of subtracting a polynomial. Say I have 1 plus x to the power 2. So there is a polynomial. It has 3 terms, so we might call it a trinomial. And the 3 terms are unlike, so I can't just collapse them down into one thing. Let's say I take that and I subtract from it. Let's say I subtract the polynomial 2x plus x squared. So now I'm subtracting one polynomial minus another polynomial. So what am I going to do? I know that the exponents are not going to change in this case. So the only things that are going to change are the coefficients in front of the respective exponents. But how am I going to carry out this calculation? What are your favorite methods? Say again? Okay, so one way to do it is to use the so-called distributive property of multiplication over addition, by which we'll turn this subtraction into addition of -1 times that quantity. Right? So we introduce this little sneaky little multiplication in front of my second set of parentheses. Because once I sneak that multiplication in front of the parentheses, it distributes across the addition that's on the inside. And so what we end up with in that case is that I'm going to be adding, there's my plus sign from the front, I'm going to be adding -1 times 2x. What's a better way of writing -1 times 2x? How about just -2x? And I'm also going to be adding -1 times x squared, which is also known as minus x squared. But once everything is addition, we can lose our parentheses because addition is associative. And so then the question is, how do I take this thing which still has 5 different terms in it and make it simpler? What should I look for? So for like terms, because we know, based on point number 1 up here, that we can add together two monomials if they are like terms, and their exponents won't change. We'll just add together their coefficients. So what's one pair of like terms in the expression down here at the bottom? Same variable, same exponent, like terms. What's one pair? So you said x to the power 2, and it matches with minus x to the power 2 from over here. So how do I add together those two like terms? How many x to the power 2s am I going to get? If I have one of them here, negative one of them here, I add those together, and how many x squareds do I have? None, exactly. So we might write it as 0x squared in that case. Okay. Find another pair of like terms. What other like terms do you see here? How about x and negative 2x? Again, I have a secret 1 in front of this one. So if I have 1x and I have negative 2x added together, gives me how many x's? Negative 1x, exactly. All right, and then I have the one thing that doesn't have a like term to match with it. Have that one.
1x, but you can say negative x, right?
Yes, you can. I'm being a little bit brutal on it right now, just to keep those coefficients in there. But now we're going to take that away when we just simplify it out. So now we combine together all the like terms. Now I'm just going to kind of prettify the expression, make it pretty. What is 0x squared? What's a simpler way to write 0 times x squared? Yeah, multiplying 0 by anything just gives us 0, right? And then adding 0 to anything doesn't change it. So in fact, we don't need to write that term at all. We have an equivalent expression whether we write that term or whether we don't write that term. So if we leave it out, we get something that's simpler, but still means the same thing. Often we call that canceling, right? 1x squared plus negative 1x squared, those two terms cancel one another out, and they vanish from the expression. And then, this is to Greg's point, negative 1 times x is probably more simply understood as, or simply written as, just minus x. And so getting rid of that leading 1 in front of that coefficient also helps us to simplify this expression some more. Can I do any better than what's down here at the bottom, 1 minus x? Can I simplify that? I can't, because those two are not like terms. Exactly. One of them has a variable, the other doesn't have a variable at all. So definitely not like terms. Great. So that gives us a method for how we can subtract one polynomial from another. Okay, well, I've left one point up here that we didn't get a chance to write in. And so I'm going to do that right now just to make sure that we're prepared for the task at hand. And that is this, that we're going to also, okay, so we've got to build one more level on top of what's on the left. One more time when exponents change. So we covered all the basic operations of arithmetic. We have addition and subtraction living over here on the right. We have multiplication and division living over here on the left. So where else could we possibly go? What other operation can I do to a polynomial that might change its exponent? Besides addition, subtraction, multiplication, and division. Last of our elementary exponent rules is what happens when we raise a monomial to a power. Raise a monomial to a power. So this is sometimes called the power of a power rule. So let's do a quick example to that end. So let's say I have, let's make it interesting. Let's put a negative 2 here. And then I'll put x to the power 3. And I want to take this and I want to raise it to the third power. So I'm raising a power to a power. Okay, so what's going to happen, do you think? First of all, what's going to happen to the exponents? What do I expect this 3 and this 3 are going to get together and do in this example? Any thoughts? That's a great guess. So multiply the exponents. Let's think about why that might be the case. One of the things we can do that we did before is we can just expand it out. Multiply the exponents. And again, remind ourselves of what it means to raise something to the third power. Raising something to the third power means that I want to multiply it by itself 3 times. Right? So this is really negative 2x to the third times negative 2x to the third times negative 2x to the third. But again, we can rearrange the order of all these multiplications to get all of my negative 2's together and get all of my x to the thirds together, so that what I have is negative 2 times negative 2 times negative 2 times x to the third times x to the third times x to the third. Why does that help? I claim this gives us something that we already know how to do. We already know how to multiply monomials together. How do you multiply monomials together? Add their exponents, exactly. So we'll just add the exponents, 3 plus 3 plus 3. But what have we done? We've added the number 3 to itself 3 times. What's another way to say what happens when you add a number to itself? Well, that is the essence of multiplication, right? That is what it means to multiply 3 by 3, is to add it to itself 3 times. So that's, again, for positive whole number exponents, a justification for why this works the way that it works. So for these exponents, I'm going to multiply. And 3 times 3 is going to give me, in the end, x to the power 9. Now, how about the coefficient? This, by the way, is also a place where brain freezes can and do happen. What's going to be in front of my x to the 9th? Negative 8. Brittany, is that what you're going to say? So why is it negative 8? What's your thoughts? You multiply negative 2. Well, you multiply negative 2 not by 3, but by itself 3 times. Exactly, right. And that's the sort of the place where your brain comes into this danger zone. If you find yourself in your head saying multiply negative 2 by 3, red flags should go up, right? Because even though I know that you knew what you meant, by the time it makes it onto your paper, it might be the wrong thing, right? So yeah, multiply negative 2 by itself 3 times. And when we do that, we do in fact get negative 8. So the exponents multiplied, but the coefficient got raised to the 3rd power. So what you notice in all the examples on the left is that the arithmetic that we were doing to the monomials also happened to the coefficients. When we multiplied monomials, the coefficients, 2 and 5, multiplied. When we divided monomials, their coefficients, 16 and 2, divided. When we raised a monomial to a power, that coefficient got raised to that power. So that arithmetic doesn't change. Whatever happens to the monomial happens to the coefficient of that monomial. But what happens to the exponent is different. What happens to the exponent is one step simpler. And the way that everything is arranged up here on the screen is a little bit suggestive. So when we multiplied monomials, we added exponents. That's because multiplication is nothing more than a repetition of addition. So it's the operation on which addition is built. And likewise, when we subtracted exponents, it was because we were dividing, because each is the opposite of the one which lies above it. So there's a bit of a relationship between these two columns. But again, the most important thing when you look back at this is to remind yourself, when do I change exponents and when do I not change exponents? And in those cases where I do change exponents, how do I change them? And all of what matters is what kind of arithmetic is happening to those monomials. In the case where we're multiplying, dividing, or raising a monomial to a power, their exponents change. But when adding or subtracting monomials or polynomials, one to another, the like terms combine, but the exponents remain the same at all times.